Welcome students, and in this video we are going to talk about the derivative of a of a function from R2 to R. So let's say you have a U which is defined on some rectangle I, okay, and this is an open rectangle for our purposes. This is AB cross CD to R is any function, okay. It need not be continuous at this point, okay. So any function. Now see, we want to talk about the derivative of u, right? Now generally speaking, in one dimension, what happens is, if you want to talk about derivative of u, you have to talk about the continuity of the function first, right? But in this case, what's happening is this. See, what we'll do is this: we start with any function, yeah, and this function, it takes a vector and put it into a real value. So please remember, it's a real valued function. Huh? We call such function as a real valued function because the value which it takes is real valued function. Okay, right. Now the thing is this: we have to understand what is the idea of derivative here. Okay, so we start with any function, not only continuous, any function. Now let's say that this function is two variable function. U is a function of x and y. Okay, now we see, let's say we define phi y of x, a new function, okay, or maybe w, let's do it like w y of x. So what is it? So basically, first of all, I will fix a y, okay. So let's understand this thing. See, this is a domain, yeah. Let's just understand this. This is a, b, and let's say this is c and this is t, okay. So this is the domain in which the function is defined, yes. Now the point is this: first of all, I am going to fix a y, okay. So let's say fix a y here anywhere between c and d. So if you fix a y, you see the function is only varying only on this line now, okay. So only x is varying. So now we have this function x and y, and for this fixed y, since y is fixed, for any fixed y, for a fixed y, and where am I taking y from? CD, right? See, y is fixed. So this function is no more a two-dimensional function but a one-dimensional function. So basically it's defined from R to R AB to R, right? So now you can think of w of y is from AB to R. See, AB to R, yeah. And now the thing is this: it may happen that this is a differentiable function. If it is differentiable, then what can we say? Let's understand this thing. Okay, so wy is from AB to R is, let's say, a smooth function, means smooth function for which, for a fixed y, in CD. Okay, so in this case I can define what wy prime of x is. Prime means here it means dx of wy. Okay, this is what it means, yeah. Okay, at the point x, of course, yes. Now what does that mean? It means that we are talking about limit h tends to 0. You see, wy of x plus h minus wy of x by h. We can talk about this. Of course, the limit exists in this case, right? Since we are assuming it is a smooth function, you do not have to assume it, but for now, let's just assume it. Okay, just to make understand what's going on. So limit h tends to 0. If you put it together in terms of u, it becomes u of x plus h acting at y minus u of xy and then by h, right? So you see this thing, if wy is differentiable, yeah, at the point x, then this exists, and we define the derivative. Okay, so basically we define the partial derivative. We write it like this: the partial derivative of u with respect to, you see here y is fixed, so with respect to x, we are looking at the variation of y in the x direction with respect to x, for a fixed y. So at the point x comma y is any point. See, this x and this x may not be same. I mean, this x signifies that we are doing it in that direction, x direction, and this x signifies that essentially we are this is a point. If you want, you can change it to x naught y naught, absolutely no issues. Okay, so how do we do it? So this we will define it to be this particular limit. So limit h tends to 0, u of x plus h y. See, y is not changing, only we are looking at the change in the x direction, y by h. Okay, if it exists, of course, if it exists. So you understand, this is just the motivation part. So this part you can think of it as a motivation. So from this motivation we can define the partial derivative of u as this. Okay, and similarly you can also fix x, and then you look at the variation with respect to y, and we can write it as del u del y at the point xy. Again, this y and this y is may not, I mean, this y signifies that this is differentiable with respect to y. So we can actually talk about the variance of u with respect to in the y direction. This y is just a point. So basically, if you want, you can write it as x naught y naught. Okay, so let's write it as x naught y naught just to avoid any confusion. So in this case, what should that be? It will be limit k tends to 0. This is h, this is k, and we can write it as u of. So in this case, you see, only y is varying. We are not really interested in x. So x remains x, x remains x naught. This is x naught, and y naught plus k minus u of x naught y naught by k. Yes. So again, if it exists, so if this limit exists, then we call this as the partial derivative of u at the point. So we call it a, so this thing we call it a partial derivative of u, okay, at the point x naught y naught, or a partial derivative of u with respect to y, with respect to y at the point x naught y naught. I hope this is clear. Again, you can put x naught y naught here, absolutely no issues here. So if you put it, it will look like this, x naught y naught. Is it okay? So just to avoid any confusion. Yes. Okay. So once this is true, let's just understand this idea with the help of some examples. Of course, you guys already, I am quite sure you know how to do all these things. This is just revision, mind you. So let's say u of xy is, let's start with a function which is, let's look at this thing. See, let's say 1 when x equals to 0 or y equals to 0 or both. Okay, and let's say this is 0 otherwise, means what do I mean by this? See, if you am taking points from this axis or origin, then if u is 1, and except that everywhere u is 0, any point u is 0, u is 0 here, u is 0 here, u is 0 here, but only on the axis. If you are standing on the axis, then it's going to be 1. Now see, this function is clearly not continuous at any point. So let's say if you start with any point on the axis, of course, any point on the axis. So let's say x naught 0, yeah, is any point on the x-axis, right? See, y equals to 0 here. So basically, let's say this is a point which is given by x naught and 0, right? And we want to see whether the function is continuous or not. So it will be a practice to check whether it is continuous or not. Okay, so do you think it is continuous? Of course not. Why? Because you see, if you start taking a sequence in this direction, so basically take a sequence which is like x naught, okay, and y naught is y, okay, x naught y, which converges to x naught 0. Okay, let, this is the sequence, let x naught y converges to x naught 0 be any sequence. Okay, so basically, sorry, x naught yn, yn, okay, any sequence. So basically the sequence yn converges to 0 and x naught yn converges to x naught 0, okay, such that yn is not 0 for all n in n, for no n in n. Okay, okay, so if that happens, then what is u of x naught yn? Okay, what is u on x naught yn? Here x naught, we are assuming it is to be non-zero, let's say. Okay, so what is u of x naught yn? This is always going to be, you see, these are points here. Okay, so this is always 0, so this is always 0, so that cannot converge to u of x naught 0, which is going to be 1. Is it understand? So this is not continuous, not continuous. Okay, fine. Now the point is this, let's just understand whether this is differentiable or not. Okay, right. So differentiable, we did not use this concept. What we are talking about is whether the derivative exists on a partial derivatives. Okay, so let's look at it. So let's take a point. Let's say we start with a point here. Okay, and so let's say maybe origin. Let's just say stick with origin. Huh? So we want to see whether del u and del x with respect to x at the point 0, 0 it exists or not. So if it exists, then this limit should exist. What is the limit? Limit h tends to 0, u of 0 plus h minus u of 0, 0 by h, right? This should exist. Okay, so what does this give me? Limit h tends to 0. You see, u of 0, 0 plus h is 0, 0 is u of h 0 minus u of 0, 0, which is 1 minus 1 by h. So which is actually 0. So this limit exists in this case. Okay, so this exists. The limit exists. Okay, so what is therefore del u del x, okay, the partial derivative of u with respect to x at the point 0, 0 is going to be 0. Okay, and similarly, can you check? So please check this part. What is the partial derivative of u with respect to y at the point 0, 0? Okay, what is it? So you see, one good thing about it is we do realize that, and you can check that this actually exists, and the partial derivative actually exists and going to be 0. Okay, so you can check that. So please check this part. Now the main important part here is this. In this case, the partial derivative of u with respect to x exists, with respect to y exists. Yes, the derivative, partial derivative, but the thing is the function is not continuous. So basically just the existence. So please remember this thing. Okay, just the existence, of partial derivative, existence of partial derivatives, okay, derivatives are not derivatives is not enough, to guarantee continuity, okay. So you do realize what's happening here is this, that this is exactly not a nice analog of one dimensional feature, because in one dimension we know if something is differentiable at some point it has to be continuous, right? Okay, so in this case what we'll do is this, I mean there is a huge theory about it, something called a total derivative and all. So what we are going to do is we are going to skip that part, we're just going to concentrate on this part. So essentially we are going to define the derivative of u, okay, in this case. So u is from where to where? From some a b cross c d to r, okay, real valued function is given by the gradient of u at that point, okay, x naught y naught, whatever that point is, x naught y naught, and let's say that will be, we will define this thing as the gradient, and we will define it like del u del x at the point x naught y naught, and del u del y at the point x naught y naught. Okay, so that is what we are going to call the derivative of u at the point x naught y naught. Okay, so of u at x naught y naught, we should write it as this. Yeah, so of course I am abusing the notation a little bit, but the thing is this is generally the case. I mean, you do not have to worry about, because we always talk about continuously differentiable function. So basically this is always true for continuously differentiable function. Whatever I wrote, this is always true for continuously, always true for C1 function, continuously differentiable. Okay, so in this context, what is continuously differentiable? It means that both partial derivative exist. Okay, so basically C1, let's write it down. So okay, with this definition, so basically the derivative what we are defining is as the gradient of u, which is del u del x and del u del y at some point. Okay, now with that being said, we are going to define something called a continuous differentiable function, which I am always saying continuous differentiable. What does that mean? It means the derivative is continuous. Okay, So in our context, what is the derivative? It is the gradient. So basically we are saying that the gradient of u, okay, and where is it defined? Gradient of u, it is defined at the c. Gradient of u is defined on x naught y naught. X naught y naught is a point in that rectangle I, okay, and it is taking that point in rectangle I and it is giving you back an element of R2. Okay, so gradient of u. So that is a function, and this is called a vector field, such functions. Okay, vector fields. Okay, and so is continuous. So basically if this the gradient of u is continuous, then u is c1 or continuously differentiable. Continuously differentiable, this is a shorthand notation which I am going to use in this course. Okay, so what does that mean? You see, gradient of u is basically ux and uy, right? Uy. Okay, so if I am saying gradient of u is continuous, that will imply that both ux and uy are continuous. Uy are continuous functions. Okay, continuous functions. Okay, so what I mean by this, whenever I am saying that a real valued function, the derivative is continuous, continuously differentiable. Okay, so a real valued function is continuously differentiable if both the derivative exist, partial derivatives of course, and they are continuous. Okay, in three dimension, u with respect to x, u with respect to y, u with respect to z, all of those three has to exist and they have to be continuous. That's all. Okay, so let's look at an example of a continuous differentiable function. Very easy. Let's say u of xy, you take it to be let's say exponential x and I don't know, maybe sine y. Let's do it like this. Okay, so what is the derivative? If I'm asking you what is the derivative of u, so what is the derivative? The question is this: find the derivative of u at the point. I mean, you can give any point, but let's just stick with for now. Let's just give it to be 1 0. Yeah, I mean, you can put any other point, doesn't really matter, but for now let's just stick with 1 0. So what is the derivative? It will be gradient of u, okay, at the point 1 0. This is what we are trying to find out. So what is it? It is actually del u del x at the point 1 0 and then del u del y at the point 1 0. That's what we need to find out. Okay, now you see what is del u del x at the point 1 0. It is, you can of course use your general, I mean, the definition which I showed here. Okay, you can use this definition, but the thing is this, we do not have to go through it. Basically here, if you want to talk about the derivative, you just, with respect to x, when I'm doing, you just fix a y. You treat the y variable, the y terms as a constant, and just the variable is the x. So in this case, what is it? The partial derivative of u with respect to x is this sine y. This term should be your constant term. Y is fixed, so sine y is fixed. So only e power x is varying. So the derivative of u with respect to x is basically e power x. E power x derivative is e power x, so it becomes e power x sine y evaluated at the point 1 0. Okay, and what is again del u del y at the point 1? See, if u is e power x sine y, okay, so del u del y will be what? It is basically, I am looking at the variation of y with respect to the variation of u with respect to y. So that means that this particular term, the term containing x, is essentially a constant. So it will remain e power x, and then the derivative of sine y will be cosine y. Is it okay? So essentially in this case, it will be e power x cosine y restricted to 1 0 at the point 1 0. Is it okay? Now, if you want to put it together, then the value which you are going to get is exponential x sine y, which is sine 0, which is 0, times e power x and e power 1. This is e times 0 and this is e power 1. Okay, so which is e essentially, and cosine 0 is 1. So this, the derivative in this case, I should write it as gradient of u at the point 1 0. Okay, gradient of u at the point 1 0. Yeah. Okay, this is your del u del x at the point 1 0 and then del u del y at the point 1 0. Okay, which is this. So this is nothing but 0, and then you have e. Okay, so that's your derivative of this particular function. Okay, so let me give you a question here. Try to find out if you can do find the derivative of this thing. So find the derivative of this function u of xy equals to x square plus e power y. Very, very simple. Find du at the point 0, 0, if it is possible, if possible. Okay, we don't know whether it is possible or not. So my question is if possible. Okay, but by the look of it, you do realize this is going to be, is possible basically. Okay, now, so this is just the first order derivative, just the first derivative, right? Now in PDEs we'll also talk about higher order derivatives. So what does that mean? It means that so basically, in one dimension, so let's say f is from AB to R, AB to R, right? And then you can talk about, let's say, f prime exists and is continuous, and is continuous. Okay, so what do we call such functions? That implies that f is continuously differentiable. So f is C1 of open AB. Okay, so this is a simple thing which we know from our calculus thing. Okay, now you see in our case what happens, this AB becomes AB cross CD. Okay, so u from AB cross CD, AB cross CD to R. Okay, so this let's say this function is such that the partial derivative, the derivative exists. Okay, what is the derivative? This is gradient of u. Okay, that exists for all points. Yes, that exists for all points. Okay, and so this exists. So basically what does that mean? That means it means that both ux and uy exist. Uy exists, okay, for all x comma y. Okay, so for ux and uy exist for all x comma y. Okay, so gradient u exists and is continuous, okay. So it means that both the functions ux and uy are continuous. That will imply u is c1. So that's just the first derivative. Now you see this gradient of u is again a function, right? Yeah, so if it is continuous, the gradient of u, if it is continuous, then it is c1 of I. We call it u is c1 of I. Okay, now if gradient of u is continuous, okay, and differentiable, so not only continuous, okay, it is also differentiable, okay, then we define the second derivative of u. In this case we call it a second derivative of u. Okay, derivative of u as d2u. We write it as d2u. Okay, so please remember this d2u in our case we will define it like this. It is u xx u xy. This is our definition. U yx and u yy. Clear? We will also call this as the Hessian of u. Okay, and of course this will be defined at some point, so it will be evaluated at that point. So basically this will turn out to be a 2 cross 2 matrix in this case. Is it okay? So in this case what is happening, the first order derivative is just the vector ux and uy, but in the second order case what we'll do is we will define the derivative d2u as the uxx, uxy, uyx and uyy. Okay, now you see, so this is a new function d2u. Yeah, d2u is a new function, and let's say this is continuous. Yeah, so what do I mean by continuity of this? It means that all these variables all these functions uxx, uxy, uyx and uyy all exists and are continuous Okay, then we call the d2u is continuous essentially. Clear? Okay, and if this happens, this will imply that u is c2. Okay, so I hope it is okay for you to understand what's happening here. First of all, let's say you have a function u, okay, and we can talk about the derivative of u, d of u. Let's say u is such that the derivative of u exists. Derivative of u exists means ux and uy exists. Okay. Now, not only exist, we say that this is the derivative is continuous. Okay. So, if the derivative is continuous, it means that will imply that u is c1. So, the derivative exists and it is continuous, u is c1. Okay. Now, u is c1. Now, if u is such that the derivative exists is continuous and the derivative map is also differentiable. So, basically, we can talk about d of du, which is d2 of u. Okay. See, I am writing at du, you can also write it as gradient of u. Similar thing, yeah, it's just a notation. So, d of du is d2 of u. Okay. So, this is called the Hessian of u, which we have just defined earlier of u. Okay. And now the thing is this, if this d2 of u, this is continuous, okay, this d2 of u is again a function, and if d2 of u is continuous, then we are calling it a twice continuous differentiable function, then u is c2. Okay, c2 means twice continuously differentiable function. Okay, I hope you have understood what's happening here. So let's take a small example and see how to calculate t2u. So let's take a simple example again here. Example. So u of xy, let's say, is 4x plus 3y square. Yeah, very simple polynomial equation, very simple, but it is just for a practice, so that you may not get confused. So first of all, how do you define? See, we want to find out what is, so d2u at some point x0 y0. Let's just find this. Okay, how do we do it? Okay, see, first of all, what we do is you calculate ux, okay, at some point x0 y0. What is ux? First of all, ux is just 4, right? Take the derivative with respect to this, which is 4, and then derivative of this with respect to x is going to be 0, so it is just 4. Okay. Now, what is uy? By the way, ux is nothing but del u del x, and then this is del u del y, uy. Let's say this is at the point x0 y0. Evaluated at the point x0 y0 and evaluated at the point x0 y0. Okay. So this is nothing but 6y. Okay. Now you see again, what is del u del x square? Del square u del x square. So basically del x of, so this is nothing but evaluated at the point x0 y0. This is nothing but del x of del u del x evaluated at the point x0 y0. Okay. What is it? So you take this function, what is del u del x, which is basically 4. Now if you are taking the variance of this function with respect to x, this becomes 0. Okay. Again, similarly here, if I want to take del y of del u del y, okay, evaluated at x0 y0, what is it? It is nothing but del square u del y square evaluated at the point x0 y0. Okay. And what is it? Okay. So essentially, what is del u del y? Del u del y is 6y. Now, if you are taking the another derivative with respect to y, it becomes 6. Evaluated at the point x0 y0, which is basically 6. Clear? Okay. So now we also have to figure out what is, you see, t2u contains this term, but uxy and uyx. Okay. So generally, del u del x of del u del y, this we will call it as u of yx. Okay. So essentially we mean this uy with respect to x. Is it okay? Okay. So what is u of yx? So first of all, you find out what u of y is. What is u of y? In this case, it is 6y. With respect to x, this is going to be 0. Okay. Again, what is del? Of course, this all of this is evaluated at the point. So the whole calculation is evaluated at the point x0 y0, which again turns out to be 0. Doesn't matter. Okay. I'm not writing all that. You can do it yourself. Again, del y of del u del x. What does that happen? Then it is basically, we can write it like this: ux with respect to y, which is u of xy. We write it like this. Okay, so what is u of x? U of x in this case is 4. So 4 with respect to y is going to be 0. So basically it is 0. Okay. So therefore, what is the Hessian of u? The second derivative. So it is given by uxx, which is, what is the u of xx? It is 0. Okay. What is uyy? U of yy is going to be, what is the uyy? It is going to be 6. There is a mistake, no? 1 second. Del u, okay, 6, huh? Okay, yeah, no mistake, C, sorry. Uxx, uxy, uxy is 0, uyx is going to be 0, and then uyy is going to be 6. So basically, this is your Hessian matrix. We call it this as a Hessian matrix. Hessian matrix. Okay, and basically this is, I mean, although it doesn't look like such, but we call this as the second derivative of u at whatever point. Yeah, I mean, in this case it is evaluated at the point x naught y naught. X naught y naught is any point in R2, essentially that, but for any point x naught y naught, basically this is this matrix 0006. That's what I'm trying to say. Okay, so I understand that you have more or less have clear idea of what's going on. Let's look at another example, not example, so I will put a question here. So u of xy, let's say, is x square minus y square. Okay, now check this whether uxx equals to uyy or not. Okay, so such a map, so let's say what will happen is this: we will define a new function. So define a new function operator, sorry, which we are calling at Laplace of u. This is called the Laplacian of u. Laplacian of u. Okay, and generally in engineering courses we also, or in physics also, we write it as del to u. Okay, but this is a abuse of notation. Please understand, abuse of notation doesn't make any sense actually. Okay, but still we just write it like this. But generally speaking, if you want to make it proper, you have to write it as Laplace of u. And what is it? It is basically uxx plus uyy. Okay, uxx plus uyy. Okay, so first of all, we have to check for, let's say uxy equals to x square minus y square. Is this true or not? Let's just check. Okay, so you see from here it is very easy to see that uxx is going to be 2 and uyy is going to be minus 2. So basically this is definitely not true. Okay, but if you are looking at uxx plus uyy, it is going to be always 0. Okay, so this actually, this uxy equals to, therefore this uxy, this function equals to x square minus y square. Okay, uh, I mean, if you think about it, it actually satisfies this relation, right? Satisfies Laplace u, which is uxx plus uyy equals to 0. Okay, so such functions, such a u is called a harmonic function. It's called harmonic function. Okay, harmonic function. We are going to talk about it in the theory of PD, but essentially that's that. That is why we need a second order equation. Okay, because you see in PD we are basically, of course we do some first order, but then the important part is the second order equation, which consists of the heat equation, wave equation, and the Laplace equation. And this is an example of a harmonic function is okay, which is basically a elliptic equation. Okay, so I hope that you have understood how to calculate this stuff. That is more than enough for now. Okay, just to finish this up, we are going to define a new concept of the directional derivative. This is very, very important because we have to define Neumann boundary condition also. So it's called the directional derivative of u at the point x naught y naught, in the direction eta, eta. Okay, what do I mean by this? See, let's say a function is defined in some rectangle here. Okay, and the thing is, so this is the rectangle, and the thing is, I take a in gamma, let's say this is gamma, this is some vector gamma which has some direction. So basically I want to see that, let's say x naught y naught is some point here, x naught y naught is some point. Okay, And if you look at x naught y naught plus gamma, uh, t times gamma, let's say, this direction. So x naught y naught, and you move towards the, in the direction of gamma. From x naught y naught, you move towards the direction of gamma, and I want to see what is the variance of u at that direction. You understand? So initially we are just looking at the direction x and the direction y. Here now we are going to look at an arbitrary direction. Okay. Now how do you calculate something like this? See, we do it like this. We call it a del u del gamma at the point x naught comma y naught. Is it okay? And we define it like this. It is defined as limit t tends to 0 u of, so let me do it this way, x naught y naught plus t times the direction gamma. Gamma direction is given as a vector, right? So it is basically gamma 1 and gamma 2. So it is t times gamma 1 and gamma 2 minus u of x naught y naught by t. Okay. So if you want to put it this way, we write it like this: limit t tends to 0 u of x naught plus t gamma 1 y naught plus t gamma 2 minus u of x naught y naught by t. If this limit exists, okay, then we call it a partial derivative of, directional derivative of u at the point x naught y naught in the direction gamma. Is it okay? So as you can check that if gamma is nothing but x0 direction, right? X0 direction, then del u del gamma at the point x naught y naught actually will turn out to be your partial derivative of x at the point x naught y naught. Okay, partial derivative of u in the direction x. And of course, if gamma is the direction, sorry, not x0, 1 0, and if gamma is the direction 0 1, then again del u del gamma at the point x naught y naught is nothing but del u del y, sorry, is nothing but del u del gamma at the point x naught y. Okay. So in this case, it becomes just the partial derivative of u with respect to y. Okay. See here, one small details I have missed. We'll always assume that the norm of gamma is 1. This is just a technical thing. You may not have to assume it, but generally in most books they assume it. So we are just assuming it like this. Okay. So what is this? This is basically a generalization of this idea of, partial derivatives. Okay. Now what is the relation between derivative and this thing? So the relation here, you have to remember this relation. You see, if u is differentiable, if u is differentiable, so basically what I mean is, in this case, okay, let's not go there. It will become more complicated. Let's say that if u is C1 of I, so there is some rectangle I where u is continuously differentiable, then the derivative of u, d of u, at some point x naught y naught, is it okay? Derivative of u at some point x naught y naught, okay, this is nothing but gradient of u at the point x naught y naught, right? This we already know. Yeah, this we already know. So derivative, this is the derivative, and we define this. So this we will call the derivative operator, derivative operator d of u, and this we will call the gradient operator. So gradient of u. Now what is the relation between this and the partial derivatives? So the relation is this, and you see del u del eta at the point x naught y naught will be nothing but the gradient of u at the point x naught y naught, that will be a vector, right, dot eta. Is it okay? So eta is the direction, okay. In our case, I just wrote eta to be gamma, but anyway, some direction eta, doesn't matter. Okay. So if u is C1, then this is true, and then this is also true. The del u del eta at the point x naught y naught will be given a gradient of u at the point x naught y naught dot eta. Okay. So again, if you want to learn this stuff, how all of this is coming together, this is a very, very interesting topic, and you can look at Rudin's book, Rudin's mathematical analysis. All of this is done there. Okay, analysis. But anyways, this is enough for you. And now I will finish this lecture with a simple question. Let's say that I give you for this function u of xy to be e power x plus y square. Okay. Now, can you find the derivative, the partial derivative of u in the direction eta, let's say, at the point 1, 1 here, where eta is the direction 3 and 4. Okay, so eta is the vector 3, 4. It has a particular direction, right? So in that direction, I want to see what is the partial derivative of, the directional derivative of u in that direction at the point 1, 1. Okay, so you fix the point 1, 1 and you stand on the point 1, 1 and you look at the direction 3, 4, and you want to see what is the variance of u in that particular direction. Okay, so find out the value here. So this is the question, and with this I'm going to end this lecture. Thank you very much.